Right. How are you and everybody? Good morning, good afternoon. I don't know what it's called. Welcome back from the holidays. How are you?
Well, good, sir.
That's wonderful. Comrades, I don't know where the others of you are, because I got numerous emails here. Numerous emails and messages on my WhatsApp, which I say people shouldn't WhatsApp me. Confusion about what's going on with lectures, what. Terrible. Anyways, I'm here now, so I thought we could have this lecture before we can even start our new suffering of the day. We should at least talk about what people were busy emailing me about this today. Yeah. All right. Yeah. But before we start, so you guys, you were confused about whether we're gonna be online or we're gonna be on campus. The thing is, we are supposed to be on campus, but the venues now, they haven't allocated me proper venues. So as you can see right now, or let me show you my face so that you can see where I am. You can see where I am. I'm in one of the labs. I'm in one of the labs here on campus. So see, that's one of the labs. I'm already here on Edgewood campus today. So yeah. So as soon as we discuss here, after this lecture, I'm gonna go down there, talk to Mr. Moodley and the one is here, the lab tech and the other guys, organize some stuff. Then at the end of the day, I'm gonna tune everybody. What was the final result of the venue and etc. Anyways, welcome back from the holidays, guys. I hope you had one hell of a good week. You enjoyed a little bit of summer, braai, swimming at the beach, etc. holidays. But hey, it's time to get cranky. It never ends, but it never rains, but it pours. It's pouring now. So, guys, last time we covered everything. I hope you're not gonna forget what is due this week. I hope you kept on checking LEarn and you know what you're supposed to answer, what is due this week, what is what. All right. So after this week's tutorial, I'm gonna upload the marks on Student Central. So as from Thursday to Friday, check your Student Central to see whether your marks are reflected there. If they are not, then you're gonna have to email me so that I can take you down and see what happened, whether I missed you or what was happening. And then there's somebody here who wants to chat with us. Saying, guys, can you hear anything? Yeah, they are replying me. I don't know about you. Are you guys hearing me or you can't?
Yes, we are.
Yes, we are.
So Luzugo, my guy, I think you need to find a better spot. Anyways, guys, now here goes. We're starting on magnets. Right. This is where we are now. We're starting on magnets. I think everybody knows what a magnet is. Right. You all know what a magnet is. You've played around with magnets when we were kids. You found them there lying on the floor. You're busy playing around with them, making them touch each other, repel each other, etc. So like magnets are like basically like charges, like protons and electrons. You see, you remember we said like charges repel and opposite charges attract, right? So magnets are like that. So bar magnets are permanent magnets. You see, there is a permanent magnet and there is a non-permanent magnet. So bar magnets, the ones that we usually saw, or the ones that are on speakers. You know, a speaker, long ago speakers used to have that big knob at the end, black magnets there. This means that their magnetism is there all the time and cannot be turned on or off. That's the problem with what with bar magnets. They already have a fixed what magnetism. Their magnetism is already sorry about that. I'm trying to annotate here. Their magnetism is already fixed, right? Cannot be turned on or off. But however, there is what is called electromagnet, right? Electromagnets, which are from the property that we once mentioned in brief, electromagnetic induction. Electromagnetic induction. Right. So now electromagnets, now they can be turned on or off. Those ones are made by you, right? It's like when you find like let's give an example of an electromagnet. It's like when you find a solenoid, right? A solenoid is a coiled wire, coiled copper wire, or any wire that can conduct electricity. All right. So when you have a coiled copper wire there, and then you're gonna have a battery, positive, minus there, right? Then when you have a battery there, then you're gonna connect that battery to a wire, right? Let's say a wire is coming in through here, right? Oh, sorry about that. Let's draw again. Okay. Let's say you have a coil like this, right? What do you have? You have a coil like that. And then on that coil, you go and have a battery. There's battery, right? And then that wire passes through that coil, right? So now, if you pass an electric current through a coil, right, move it up and down, a copper coil which is carrying current, and then another one carrying current, you produce what is called electromagnetic induction. Have you ever heard about the situation of ESCO? Okay, let me start with, let me use ESCO, where these water turbines, right? These water turbines, water flows down an incline like this, and then it pushes on turbines here, right? When it pushes on turbines here, there is a current, there is a coil here, right? So when you produce motion here, right, and then there is a magnetic coil inside here, this motion, right, which is producing movement around what a magnetic field, it produces an electric current. So the opposite is true. If you don't have a magnetic field, but you have a current carrying wire, which is around like this, and then you have some motion, right, you produce a magnetic field. Vice versa is true. That's what is called electromagnetic induction. So in other words, permanent bar magnets, you cannot change them. But an electromagnet now, you can turn it on or off. It depends on you and what you are using, right? And usually electromagnets, they are more powerful than this. I'm sure all of you have watched that movie. What is it called? Fast and Furious, the latest one. Is it Fast 9? Something like that. Fast 9 or is it 10? I don't know. The latest Fast 9, right?
9.
Yeah, the Fast 9 one. Didn't you see where those two guys are? For those who watched the movie, who's that Ludacris? And the other guy, they were in the van, and then they kept on asking that girl to turn it on and off.
Yeah.
Like, this is really, really annoying. Who's this? Guys, mute yourself. It's really, really annoying. Guys, I can hear your echo in my ear. So that's an example of electromagnets that was there in that movie, The Fast 9, where they switch it on and off, right? And then it goes on and then it goes out. So did you see how powerful of a magnet an electromagnet can be? Because once they turned it on, it will actually disturb many things, take out cell phones from people's hands, etc. There is another movie again, if you are a person who likes to see what we're talking about. That movie, what is it called? It's about this other guy, I've forgotten his name. I'll tell you so that you can research and see how electromagnets are big, where they built another big electromagnet, but that one, they were using it on a boat. So power magnets have two poles. There's a north pole and the south pole. Just like there's a positive and a negative end on electricity charges, right? So exactly opposite poles attract and like poles repel. That's how magnets behave. If a permanent magnets are repeatedly knocked, the strength of their magnetic field is reduced. You understand? If permanent magnets are repeatedly knocked, that means they make them hit each other. The strength of their magnetic field is reduced. Right. So converting a magnet to a non-magnet is called demagnetization. Right. Converting a magnet to a non-magnetic is called what? demagnetization, right? So the properties of magnets. Magnets are made from magnetic metals, e.g. iron, nickel, cobalt, right? These are the only pure metals that can be turned into a permanent magnet. Do you understand? Especially iron. These are the only pure metals that can be turned into a permanent magnet, right? Steel is an iron, as an alloy of iron, so it can also be. Do you understand when they say it's an alloy? When we say something is an alloy, that means it's a mixture, right? It's a mixture of other metals. So steel is an alloy of iron, and so can also be made into a magnet. Yes, that's true. So if these metals have not been turned into a permanent magnet, they will still be attracted to a magnet if placed within a magnetic field. Right? Obvious, we've tested that magnet is attracted to steel, iron, nickel, copper, any metal which is close. Right? Only a few which cannot be attracted to a magnet. So in this situation, they act as a magnet, but only whilst in the magnetic field. This is called induced magnetism. You understand what they mean? They mean now, if you have a magnet, this is a magnet, and then you have a coin stuck onto it. So as long as that coin is stuck on that magnet, it's also magnetic during that time. Wow, because of this magnet, it's induced magnetism, that one. It's not permanent. When you take it out from there, it becomes the coin itself without any magnetic properties. Now, substances that can be permanently magnetized are described as magnetically hard, right? These are often alloys of what? Iron, nickel, and cobalt. Substances that can only be temporarily magnetized are described as what? Magnetically soft. So you gotta take note of these terms, right? So that when those multiple choice questions come on your tutorials, you don't get confused. You know, it's clear cut what you're talking about. Alloys with less iron, nickel, or cobalt would be magnetically soft and have a weaker magnetic field, right? And then alloys of iron are called, this we discussed, they are called ferrous metals. And those without iron, it's non-ferrous, right? Ferrous metals meaning they have iron, Fe, chemical formula name. Non-ferrous, no iron. Testing a magnet. Now, here is a test that you can do. You can't test what the magnet is attracted to, but you can test what it repels. Objects that are made of unmagnetized iron, cobalt, and nickel are attracted to either pole of a magnet, but not repelled. You can only show that an object is a magnet if it repels another magnet. Take note of this statement here. You can only show that an object is a magnet if it repels another magnet. You understand? If only it repels another magnet. But without that, you cannot say this object is a magnet. So is what no. That's the only test that you could do. Now the comrades so far okay. Hopefully. Someone is trying to speak Penoid.
Oh, sir, can I please? Oh, thank you, sir. Can I please ask?
Yeah.
Can't we like test a magnet by repairing it against what Mencel?
Against what?
Mencel.
Metal.
Yes.
No, you can't, because a metal will always be attracted to a magnet. It doesn't care whether it's a south pole, it's a north pole, it's the side body, it's whatsoever. It gets attracted to a magnet. Just take a coin, spin the magnet around, see if it won't be attracted to the magnet. It will. But if you bring another magnet, it will be attracted at certain ends. On other ends, it will repel, showing you that this is the north or south pole. So that's the only test that you can do to check that a device or metal that you're carrying is a magnet. You test it against another properly made magnet, bring its north pole or south pole, then spin it around, see if it gets repelled. If it doesn't, it's still attracted on all sides, then that's not a magnet.
Okay. Oh, I now understand. Thank you so much.
All right, cheers. All right, let's continue there. So we're talking about now magnetic field lines. Magnetic field lines are like electric field lines. So remember, when we talked about an electric field last time, we say the electric field have lines. Magnetic field also have lines. So magnets create magnetic fields. These magnetic fields cannot be seen exactly like the electric field. You cannot see, but it's there. Although we cannot see magnetic fields, we can detect them using ion filings. I'm sure you've come across this thing in primary or where you use ion filings, and they make nice lines there. Or you can take a piece of paper, you know, when you have a crushed magnet, crush some magnet, and then those small pieces of magnet, once they are crushed, put them on top of a paper, and then put another magnet under the paper, and then another magnet on top with your hand. They will align themselves properly, giving you the direction of the field. So although we cannot see magnetic fields, we can detect them using our ion filings. The tiny pieces of ion line up in a magnetic field. So these magnetic fields will fill the space around the magnet where the magnetic forces work and where they can attract or repel magnetic material. So you see what we're talking about. This is how, I'm sure you guys have tried it before. When you've crushed magnet, you've played around with a magnet at all. This is exactly how they line themselves. You see how they did. That's how these are the magnetic field lines. These are the magnetic field lines, as you can see. So they keep spreading and spreading and spreading. They go like this, like that, like that, like that. So you remember an electric field, for an electric field, it was different. They were going in a straight line like this. Look at the magnetic field ones. They're kind of like oval shaped, like. So drawing magnetic field diagrams, a bar magnet with several curved lines pointing from the north to the south pole. You see, they are kind of oval shaped. In the center, more like an apple, as you can see, more like an apple, right? They come out, check the direction. They come from the North Pole to the South Pole. So the arrow is pointed away from the North Pole, but towards the South Pole. See, that's the direction. So take note of that. It's different from the electric field because the electric field was just straight lines. But this one now is the opposite. It's oval shaped lines, almost circular, from the North Pole to the South Pole. You know, somebody asked me during the holidays about the magnetic field of the Earth, and I was like, Miner, do you think we can make use of the magnetic field of the Earth? And I was like, no, because the magnetic field, the Earth's magnetic field is strong. Yes, it's really strong because we can use it like compass on your phone. You see your phone, you guys are nowadays, you grew up in the nowadays when phones have compasses and stuff. You never used the old instruments like some of us. Some of us are now ancestors, you understand? We used to use neatly compasses to actually find the North or the South Pole. You guys, you just take out your phone, you use Google Maps and stuff like that. But one day when Google Maps gets you stuck in the bundles, what are you going to do? That's when you're going to now open your phone, open the compass there. But if your battery goes out again, what are you going to do? You're stuck now. That's when you're going to come to the old methods of ours, of taking a needle here in the cut box, trying to magnetize your needle there, and then placing it nicely and checking the direction of the North Pole, whether it will work. So some of us grew up in the hey, I don't know. But you guys are lucky because you just do. So someone was asking me about the Earth's magnetic field, how big and how useful it can be. That one I can't fully answer as I answered you that it's not strong enough. It's strong to actually guide, like be part of the navigation system of ours and etc. But in terms of like properly being utilized as a magnetic field to work on something, it's not that powerful. Hence, human beings created electromagnetic fields so that those ones, they can strengthen the field to magnify it and do whatever they want with it. Sorry about that. Now, in the diagram note, we've talked that the field lines have arrows on them. The field lines come out from the North Pole and going to the South Pole, yeah? the fault lines are more concentrated at the poles. Yes, the magnetic field is stronger at the poles where the fault lines are most concentrated. You must also take note of this, that the magnetic field is strongest at the poles where the fault lines are most concentrated. But we've discussed all of this. So for example, now let's check out two bar magnets. Note the different patterns seen when two like poles are used and two opposing poles are used. For example, look, when it's north and south pole, you see the field just goes straight to the south pole. Let's annotate. You see the fields are going straight to the south pole, and whenever they can come out to come to the other south pole, they can, as you can see, represented by that, right? But now check when it's two north poles. Two north poles, they are repelling each other here, right? You see, they are repelling each other. They are forcing each other to go in opposite direction instead of coming to each other like the north and south pole. So note the different patterns seen when two like poles are used and two opposing poles, right? So even for a south pole, if you spin it around, right, it's gonna be repelling each other. They are trying to come to each other, right? So it's like they are fighting with each other, right? Now, let's come to electromagnets. This is the most important thing. This is what the ESCOM is crying about. When they are busy saying, the generators are dead, the generators broke down, etc., all those stories. This all starts from this principle, right? Electromagnets and electromagnetic induction. This is where it comes from, this stuff. This is where exactly it comes from. Right. So electromagnets, and electric current in a conductor produces a magnetic field, right? This is going to lead us to motors and whatnot. So an electric current in a conductor produces a magnetic field. Electric motors and loudspeakers both use electromagnets. These are made by a coil, by coiling a current carrying wire around a magnetic core. So, right, here we have a magnetic core, we have north, we have south, right? We coil a wire around here, right? And when we coil that wire, we connect it to a battery or any other source. So this is a current carrying conductor, which is coiled around the magnetic core. There is a core, right? You produce what is called an electromagnet. So there's what is called, is it lens? Or this, by the way, was done by Faraday. This is the law of electromagnetic induction is called Faraday's law somewhere there. So now, with electromagnets, when an electric current flows in a wire, it creates a magnetic field around the wire. By winding the wire into a coil, we can strengthen the magnetic field now. Hence now, electromagnets are made from coils like this. So we can make an electromagnet stronger by wrapping. So this thing is like this. As I drew it, I drawn it like that. And then we put the current conductor there, and then we can connect it there. So we're saying now, this is plus minus. This here is an electromagnet. Right. So you can say this strengthens the magnetic field of this thing, the core that is inside. But we can make the electromagnet stronger by what? Adding more coils here. If we add more coils on the core, the magnetic field will be stronger. Right. If we increase the current here, we're making the magnetic field stronger. Right. So wrapping the coil around an iron core, first we have an electromagnet strengthening the field. If we add more coils now, we're increasing the field again. If we increase the current, we're also strengthening the field again. Now, here comes an example of a nail. So you have an iron nail now. This is an iron nail. Remember, we say now iron is one metal which can be magnetized easily. It's what magnetically hard. right? That's what we say, magnetically hard. That's a strong element for making magnets. So now, if we take an iron nail like this one, right? Then put a coil around it, right? And then after putting a coil around it, connect it to a cell or battery as shown on the picture, and then put on a switch. You will find out when you close the switch there, this iron becomes a magnet, which is called an electromagnet. So you see what we've done here. We had an iron nail, which wasn't what? A magnet. It was just a metal which can be attracted to magnets or not. But then when we connected the coil around it and then we put current on it, we produced an electromagnet, produced a magnetic field around the iron. So you can feel that it's going to be attracted to other metals, pulling them closer to each other. So now you found out a way of creating a magnet. Creating an electromagnet. See, so these are some of the questions in theory that are going to be coming. Like if you, how do you create an electromagnet? What makes the field stronger? Blah, blah, blah. These are kind of the things that you need to look at them as a teacher. Let's say now you're in high school, now you have to create a lesson plan, right? What do the students have to understand about what I'm doing here? What is it for? What uses are these things for? So this is how you're gonna be planning your pracs. This can be a prac, showing them that you can create a magnet out of an iron nail. At the end of the day, you want them to know about magnets and electromagnets. You want them to know about how to increase or decrease the electromagnetic field. You are trying to make sure that whenever they get lost in the bundles and they have a cell phone battery and iron nail and whatsoever, they can create a magnet. After creating that magnet, they can place it on a cardboard box or on water if it can float, or put this nail or pin. You know, a pin, a small silver pin, those ones which are used for clothes. You can magnetize it. After magnetizing it, put a cork, you know, a cork, that one for fishing. Clamp it onto a cork and then throw it inside the water bottle. This is a water bottle. Let's say you have a water bottle like that, and then pour water and then put your pin onto a cork. It's floating on top there of water. If it's magnetized and you make it stand on a flat surface, it will point to the true north of the earth. And it will show you the true north and the true south. Then from there, you have your directions if you're lost in the bundles. You now know where north is, you now know where south is. You now know where you need to go, east or west. East is what is on your right, west is on your left hand. Once you identify north, you have your east and your south and your west. So these are the simple things that you can actually do and help yourself. There is another TV series again, which is a girl trying to use a pin to actually find their way home. She was stuck in the bundles. So these things are quite useful, even though you take them for granted. There's someone who's asking a question there. Pilanyenkos is saying, say, how is the need becoming a magnet since the coil is insulated? Let's explain this again. You know, electromagnetic induction, I don't know whether the science that I'm about to unload here, I don't know whether I'm allowed to do it. But when current flows around here in a wire, right? First, let's go back to the break and let's try to explain it this way. They said when an electric current flows in a wire, it creates a magnetic field. This is called Faraday's law. It's from the laws of electromagnetic induction. It's a fact that was discovered long back, that a wire which is carrying an electric current, it produces a magnetic field around it. Just current flowing through a wire, from even that electric cable that you have at home connecting your TV, when you switch it on, that wire there, which is insulated, it is a magnetic field in it. But just because we put plastics, right? We put plastics on top of rubber and stuff around it, so that that magnetic field which is created there doesn't interfere with the electronics. If you want to prove that this thing is there, that's why most of the times, especially older TVs or older models, and your cell phone, if your cell phone was there, you'll hear it interfering with the TV. Nowadays, it's better on TVs. But if you're calling a radio station or you're calling someone, or right now, if I'm talking to you and an electric current, I bring it closer here to my phone or etc., you'll hear the effects of like a mouse, click, click, click. Those are electromagnetic fields interfering with each other and then interfering with the electric current flowing there. But just because we are insulating with plastics, right, or rubber, we're trying to curb that magnetic field from being exposed or interfering with others. But now, on your question, this iron nail and this coil of insulated wire, we don't say insulated meaning a rubber or plastic here. We don't mean a rubber or plastic on this one. No. Have you ever seen that these wires are kind of like, I don't know what you call it, it's copper, kind of a color. I'm blind, I'm color blind. So some of the colors I don't know. Do you know the color of copper? What is the color of copper called? Okay, never mind. If you see an exposed wire, it doesn't mean that wire is bare. It's painted with a certain coating inside. It's called an insulation coat. It's a coat of insulation. If you try to peel it, that insulation comes out. It's like paint or something. That's the kind of insulation they are talking about here. They are not talking about the rubber, which is covering charger cables or bigger cables. No, it's that coating of paint that they are talking about, and not the insulation that you're thinking about. So it's not the real insulation that kept the electric current from producing what it's supposed to do there. Somebody else put another question. So how do electromagnets differ from bar magnets? We've already said it. They are stronger, they can be made stronger or weaker. You can turn them on or off, but bar magnets you can't. So the magnetic field around an electromagnet is just the same as the one around a bar magnet. It can, however, be reversed by turning the battery around. So you remember, electromagnets now, you can actually change. This is your battery, your plus or minus. You can change the polarity of the electromagnet by swapping your battery around, making this the negative, that the positive. So unlike bar magnets, which are permanent magnets, the magnetism of electromagnets can be turned on or off just by closing or opening the switch. We'll say that relays are electrically operated switches. They use an electromagnet, often to control a high power circuit. This is an example of how electromagnets are used. I'm sure you've heard of a relay, and we talked about the relay before I left, before we went for some break. We said you can use a relay to switch on higher electricity. For instance, we said you can switch on a generator using a relay, switch off and on a generator using relay. Because a relay is simple, an electrical switch which operates like an electromagnet. When current is there, on, switch connects. When current is not there, off, it's off. Okay, what's the time now? Time flies, but we still have too much. Now, this we've also talked about. We say the magnet and the coil of wire can be used to produce an electric current. That's the electromagnetic induction, what we've been talking about. Right? A magnet and the coil of wire can be used to produce an electric current. This is what ESCOM does. They have a magnet, they have turbines, right? Then they push those turbines there around. When the motion in there is turning around a magnetic field, it produces an electric current. Right. So a magnet and the coil of wire can be used to produce an electric current. A voltage is produced when a magnet moves into a coil of wire. This process is called electromagnetic induction. So hence, you know, once you create an electric current, there is a potential field. There is the electric field, so there is a potential field. That's obvious. Hence, they are saying a voltage is produced when a magnet moves into a coil of wire. The process is called electromagnetic induction. So the direction of the induced voltage is reversed when the magnet is moved out of the coil again. Yes, that's what we're talking about previously on the last slide, when we can say it can reverse the polarity or change it around. So it can also be reversed if the other pole of the magnet is moved to the magnet. That's like changing the magnet's polarity. Instead of entering the north first, you use the south to go in first. That means you have reversed the polarity there. Now, if the coil is part of a complete circuit, then a current will be induced in the circuit. Right? So if the coil is part of a complete circuit, then a current will be induced in the circuit. Notice that no voltage is induced when the magnet is still, even if it's inside the coil. Do you understand what they are trying to say? English, which people always laugh about and say, we don't know English. Notice that no voltage is induced when the magnet is still. What they are trying to say, when the magnet is not moving, because we said the magnet should be moved up and down a coil, or it should go up or down or rotate or whatsoever. But if it's not rotating or moving, it's just standing still, then nothing will happen. No voltage is induced. That's what they mean by that statement there. If it's standing still, not moving, then nothing happens. So to increase the voltage, you have to move the magnet faster. I hope you see this point. You have to move the magnet faster. This one we mentioned, add more turns to the coil, increase the stroke of the magnet. That's to increase now the induced voltage on that produced field. Oh, so tight. So a bar magnet rests outside the wire coil connected to an ammeter showing no current. You see now what they were saying. If this is still not moving, sorry, I zoomed too much. If this is still not moving, no reading on the ammeter. But if however we move this faster, then you start to see the ammeter showing us negative, positive, of the current being induced in the coil. That's what we are trying to show us there. So, comrades, so far, so good. Are the comrades okay? Comrades, are you okay? Because you can see now the explanation when they are now moving the magnets faster. You see the reading has changed. Last time it was on 0 because the magnet, this one wasn't moving. Now they are showing movement. You see faster movement towards that direction. Look, there's a reading now on the ammeter. That means moving the magnet up or down, it induces an electric field around the current around the wire there. Hence, you can see read it or measure it using the magnet. But if this is not moving, nothing is going to be read. The magnet is stationary within the coil. There is no current flow. We mentioned that. It's just a repetition now. The magnet moves out of the coil, the wire, and the ammeter registers negative current flow. All right. So that's another thing. You see now, it's the opposite movement in the opposite direction now. Since it's in the opposite direction, then voila, that's what happens. So guys, I'm done with you for today. I can keep continuing, but welcome back. I'm done for you for today. I'm gonna move out of the lab. There are people coming in here now to take over their space since I haven't been allocated my own venues. So after my meeting here, my discussion with Moodley, I will then email the class. So look out for the email today. It might come in the afternoon, it might come in the evening, but just look out for an email today. That's gonna tell us how we go forward from now onwards. By the way, I saw people were trying to find out who's the class rep. Did you by any chance identify the class rep? Hey, comrades.
No.
Okay, once you identify the class rep, tell me. Let me go, guys. People want to come into their venue now. I'll post this video lecture later and email the class.